So let's talk a little bit more about nuclear stability. I said if we were to talk about atoms that have lots of protons and neutrons kind of added in together, that the nuclear strong force is going to have a hard time holding them together simply because the nucleons are relatively far apart. And I always like to think of this as like a big bowl of jello or something like that. If you go ahead and you slap it, it's going to wobble, 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 wobble. And maybe it's even going to spit off a particle or a chunk of jello in order to shed some of that energy. We call this radioactivity, and that's just the decay of unstable nuclei. And it's going to emit either a particle or some electromagnetic radiation, and I'll talk about more of those on the next slide. Now, an Italian scientist by the name of Emilio Segre came up with a chart that plots the proton number on the y-axis and the atomic number, or Z, on the x-axis. And so here we are kind of looking at this chart right over there. So here we have N, here we have Z, so atomic number is increasing, increasing, increasing. And if we were to plot, the real elements right over here, something you're going to kind of notice is they deviate more and more and more from kind of this line of stability where N is going to be equal to Z, or equal number of neutrons and protons. And as it gets further and further and further away from it, it's going to become more and more and more unstable. So it turns out right about here, about atomic number 83, is going to be a line where we say anything above this line, anything up here is going to be unstable. So that's why things like uranium, plutonium, some of the funkier named elements are going to be unstable and not last very long. Something else is as we try to create newer and newer elements, we're essentially trying to cram more and more and more protons and and neutrons together. These guys can only be created in a lab. They're not going to occur in nature, and they're going to last for like milliseconds, femtoseconds, microseconds, something along those lines. This is kind of the reason behind all that. So really quick, popping over to the atomic table, I said that Z is equal to 83 is going to be the last stable element, and that's bismuth. Polonium is going to essentially be radioactive. Kind of work our way, kind of see that here we have radon, that's definitely going to be radioactive. You might have heard of radium right over here, that is also radioactive, and some of the other things, uranium, plutonium, thorium, cerium, stuff like that, these guys are all going to be radioactive. Anything with an atomic number or number of protons larger than 83. So let's talk a little bit about the particles or electromagnetic radiation that can be emitted from something that is inherently radioactive. We can have a sample of radium. We know that guy is radioactive from its atomic number. If we were to put that in a lead block is going to isolate it and just kind of let it spit out some radioactive things. We would see a couple of different types of radiation. First, we would see alpha radiation, just that little A right over there, and that is just a helium nucleus, so essentially it's going to be He42. It does not have the electrons associated with it, so it will have a +2 positive charge. And if we were to put a magnet around this guy, you'd see this guy kind of bend off in that direction. So we can use a magnet to separate out the various forms of electromagnetic, or the various forms of radiation. Now, something else we may see is going to be what's called beta radiation, and I stole this from a lower level physics textbook. So it is more than just negatively charged particles. It could be negatively or positively charged electrons. So we could have an electron that comes whizzing out of that, or we could have something that's called a positron, which is essentially going to be an electron mass with a positive charge. So if we were to write an electron like this, we could write a positron like this. Now, I will apologize for the confusion. You will see this as beta minus decay, which is essentially written the same way, and this could be written as beta plus. And so an electron would go the opposite direction of a proton, so this guy would kind of whiz off like this. A positron would whiz off in that direction because it has a positive charge. It's a little bit lighter than a helium nucleus, so it's going to bend a little bit faster. So this would be beta plus, and this would be beta minus. We could also emit some electromagnetic radiation, and it turns out that it's going to be a very high frequency radiation, so it's going to be what we call a gamma ray. That's the guy that looks like a fish on its nose, and because it is electromagnetic radiation, it doesn't have any charge associated with it, so it won't be able to be bent with a magnetic field. How much energy do these various particles have? Suppose you had a radioactive source and it was emitting all forms of that radiation. Alpha particles are going to essentially be able to be stopped by a piece of paper. Beta particles can be stopped by a piece of aluminum, and gamma radiation will be stopped by lead. And this is also why whenever you get an X-ray taken or something like that, they use lead to cover, let's just say, your sensitive parts, because lead can definitely stop gamma rays. It can also stop X-rays. They have less energy than X-rays. We don't want to have radiation hitting our DNA and essentially damaging the structure of it. Now I'm going to go into more detail about the various forms of radioactivity. However, I thought it'd be kind of useful. This isn't in the book, but I kind of put it together. It's kind of a chart that summarizes radioactive decay, and we can essentially look at the element before and the element afterwards, and that'll tell us a little bit about the type of decay that occurred. So for alpha decay, it's going to emit a helium nucleus. That's going to drop the mass number by 4. It's going to drop that number right there by 4. And it's also going to drop the atomic number by 2. So changing the atomic number is going to be dropped by 2. Beta plus is not going to change the mass number. It's an electron. And it's going to change the atomic number by 1. I'll talk about why that is in a little bit. Beta minus is not going to change the mass number. It's just an electron. It's going to change the atomic number by plus 1. And gamma is going to essentially not change the mass number nor change the atomic number, so it's essentially emitting a photon. So let's start with alpha decay. Again, an alpha particle is just a helium nucleus, no electrons associated with it. And if we were to look at radium, it's going to be element number 88 with a mass number of 226. You can kind of picture this guy right over here as being a nucleus that has some extra energy. We could even pretend that inside of this guy there is a helium nucleus that's kind of bouncing back and forth, and it's bouncing back and forth inside of a potential well. So here we have a potential well as a function of radius, and this alpha particle is going back and forth, back and forth, back and forth, back and forth, and if it gets enough energy, or if it has enough luck, then it can actually tunnel through this potential barrier. So this is being able to break free of that binding energy, and then the helium particle is going to shoot off in that direction right over there. Of course, energy is released by that, and I'll talk about that in a little bit. And as I said, it's going to drop the mass number by 4, just like that, and then it's going to drop the atomic number by 2. So you take a look at the table of elements, and you see that it's going to turn it down into radon. Now this radon, it turns out, is actually going to be radioactive, and you can see this right over here by the star that's right next to it. So essentially whenever we write something like radon with a star 222 as well as 86, because it is radioactive, it's going to have some extra energy associated with it, and it's actually going to emit a gamma ray. It's going to be some form of electromagnetic radiation, and then it's going to drop down into radon, which is going to have a slightly lower energy. It's emitted some energy. Keep in mind this is still radioactive, and now it can decay into other elements. Maybe another fancy word for that, this is going to be the transmutation of the elements, going from one element to the other. And this is kind of what alchemy was all about, right? Trying to turn lead into gold. It turns out you can do it, but it costs more than the gold is worth, and you end up with radioactive gold. Whenever we emit any type of particle, we're forming a different element. We're going to have a change in the atomic number. So very simply, we're going to call this transmutation, and it turns out this can occur naturally, or we can initiate it artificially by bombarding something that we know is radioactive with some energy, with some particles. So we could shoot alpha particles or beta particles or even photons at something, and it's going to initiate the decay. So again, just some more practice using this. If we had something like uranium, it's going to have 146 neutrons and 92 protons, giving us a mass number of 238. If this guy were to spit out a helium nucleus, it's going to drop that number by 4. It's going to drop that number by 2. And we're left over with a helium nucleus that comes shooting out like this. And yes, this guy does have energy. And because it dropped the atomic number by 2, it's going to go from uranium to thorium. So we're going to be breaking out a periodic table quite a bit in this chapter. So let's take a quick look at the alpha decay we looked at a little bit earlier in example 43.5. We talked about radium going down into radon, emitting a alpha particle as well. Let's calculate how much energy the alpha particle is going to have, and we're again taking a look at kind of the mass deficit. So if we knew that radium had that mass, and radon's going to have that mass for just a neutral atom, what we can kind of do is we can say, hey, this is the mass of the radium, and we can subtract the mass of the radon plus the mass of the helium particle, so this guy right over there, and realize that there's a mass deficit. And again, we really need to keep all of our digits right here to be able to see this. It is there, but it is small, so it's a 5 thousandths of an atomic mass. So what we're going to do is we're going to say, okay, the energy that is released is going to be equal to mc squared, where this guy right over there is going to be c squared in the language of electron volts per atomic mass. You can see that we're going to have about 4.8 mega electron volts that is released. Keep in mind that momentum is also conserved, so as the alpha particle goes in that direction, then the daughter nucleus, the radon, is going to go in that direction, and because it's a lot larger, it's going to be moving a little bit slower, but momentum is also conserved. So now let's talk a little bit about beta decay and gamma decay, and I'll start with gamma decay just because it's pretty straightforward. Gamma decay, what's going to happen is the radioactive substance is going to emit a photon, and how much energy is released is going to be directly related to the frequency. By our old friend, energy is equal to Planck's constant multiplied by the frequency. So we're talking about very high frequency photons here, much higher than even X-rays. For beta decay, there's going to be three types. There can be beta minus, beta plus, and electron capture. And kind of for the sake of brevity, I'll skip electron capture. You can read about that in the book. For beta minus decay, the ratio of the neutrons to the protons is going to be too large. So it's going to be very, very, very large. And what's going to happen is one of the neutrons is going to spontaneously decay into a proton and an electron. For beta plus decay, the ratio of n to z is going to essentially be too small, and one of the protons is going to turn into a neutron as well as an electron with a positive charge, or a positron. So kind of what we're going to say is beta minus decay is going to occur when the mass of the original atom is larger than that of the final atom. And kind of in equation form, a neutron inside of this atom is going to spontaneously decay into a proton and a beta minus particle, which is also an electron. Something else that's going to kind of come spinning out is going to be a subatomic particle that is actually called an antineutrino. And antineutrino is going to be something that has very little mass and no charge. And we'll talk about the antineutrino a little bit more in the next chapter. For beta plus decay, what's going to happen is a proton is going to spontaneously transform into a neutron and then a positron, which is essentially going to be an electron with positive charge, so the mass of an electron and the charge is going to be positive, and it's going to also spit out a neutrino, which is going to be kind of the opposite of an antineutrino. You can kind of see that this fits into the table in that the number of neutrons is going to drop by 1, the number of protons is going to increase by 1, so the atomic number goes up by 1, and the mass number is going to stay the same. For this one, the number of protons drops by 1, the number of neutrons increases by 1, and the atomic number is going to stay the same. So let's take a look at the transmutation of elements now using beta decay. This will be an example of beta minus decay. And in this case, if we were to start off with something like thorium is going to have 90 protons and 144 neutrons. We're going to write this guy like this. I'm also going to write it like this, and talk about why that is in a little bit. And it's going to, in this case, spit out an electron, also known as a beta particle. And what's happened here is one of these neutrons right here has spontaneously changed into a proton and an electron. So you can see the number of protons went up by 1. You see the electron kind of whizzing off right over there. Now this changes it from thorium to protactinium, so you can kind of see that number of protons went up by 1, mass number stays the same. And this is the beta particle, which is essentially saying that it has no mass and negative charge. You can also kind of write this guy just like this. I took this out of another book, so it can be written several ways. They're really both kind of equivalent. Now let's just take another quick look at how we can write alpha, beta, and gamma decays. We've talked about this alpha decay and this beta minus decay when we go from uranium to thorium, and then have the beta decay right here. Sometimes you'll see this written like this, where it's just kind of shorthand. Rather than writing the alpha and the beta minus right here, they're written simply on top of the arrow. It's pretty much the same thing. And we can also show kind of gamma radiation, where the little star means that it's radioactive, and then it's going to emit a gamma particle right over here, or some light, and we're just going to write the gamma right over there rather than writing it over there. Pretty much the same thing. I personally prefer this look a little bit better, but you'll see it written as either way. Now, what does this look like kind of graphically? Again, we have our number of protons and we have our atomic number, so the same type of plot. And we're starting right here at uranium-238, and then we have an alpha decay down to thorium. One thing to kind of keep in mind is this takes about 4.5 billion years, so you can kind of see the time that it takes for these decays to occur. And then we're going to be looking at kind of 2 beta decays going down to another isotope of uranium, uranium-234. And again, well, these are relatively short, about a month or so. And then we're going to go back down to thorium, so kind of some alpha decays. And then it's going to be alpha, alpha, alpha through radium, radon, polonium. We have a couple of paths down here. We have some radioactive lead, and then we can have some beta decays, and you kind of see it work its way down. Keep in mind that we're talking, this is 10 to the 5th billion years, so a little bit less than a million years, several hundred, or it's like 75,000 years, 1,600 years. So as uranium works its way from uranium-238 all the way down to lead, it takes a really long time. And it's going to do so through a series of alpha and beta decays. So let's talk a little bit more about how long it takes for uranium to decay to thorium, or pretty much any element. And to do that, we need to talk about activities and half-lives. And what a half-life is just the time that it takes for the number of radioactive nuclei to decrease to half of the original number. And it's going to be kind of an exponential. It's going to look like this, just right over there, where this is the number of radioactive nuclei at any given time. That's the original number. And it's going to be an exponential that's going to depend on this sky lambda as well as time. We could also say that the number of nuclei are directly related to mass. So if you had, say, a kilogram of radioactive uranium, how long does it take to drop down to half of a kilogram? And it's kind of an average thing, and that's going to be the same to go from half to a quarter of a kilogram, and a quarter to 0.125, and so on and so forth. You can kind of see cutting in half, cutting in half, cutting in half. It never will actually reach zero. So the half-life is going to be the t to the 1/2, and that's going to be in seconds or years or what have you. And that's just going to be the natural log of 2 divided by lambda, where what lambda really is going to be kind of the ratio between the number of decays per second to how long or how many nuclei are kind of left remaining. So let's flip back to the previous page, and this t to the 1/2 is going to be 4.47 billion years for uranium. We're going down into thorium. This one is going to be 24 days, 70 seconds, and so on and so forth. And you can kind of see that if we were to plot this guy right over here, it's going to be a nice, pretty exponential. It's going to decrease, 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 and never actually reach zero. Something else that is of interest is something called the activity, and that's going to be how many decays are occurring per second, or essentially a dn dt, and that's going to be related to lambda, as well as how many nuclei are left. So this guy right over here is called the activity, and you can see this in decays per second. Other common units of this guy, you're going to see these guys. One of them is going to be the Curie, which is going to be abbreviated CI. And that's a huge number of decays per second, and that just kind of makes the number slightly more palpable. And if we were to talk about this in the SI unit, it's going to be a becquerel, named after the fellow I talked about on one of the first slides, and it's abbreviated BQ. And essentially 1 Curie is going to be 3.7 times 10 to the 10th becquerel, or decays per second. Something else we may also see is going to be T mean, which is just going to be the half-life divided by the natural log of 2. And as I said, this is all kind of probabilistic, and we can't say that it's going to be exactly 4.47 billion years to go from 1 kilogram to 0.5. It's going to be roughly on average, but it may happen a teeny tiny bit faster. It may happen a teeny tiny bit slower. Maybe there's going to be 0.55 or 0.45 kilograms at the half-life. And so we kind of define this mean life right there.